Testing, testing, 1, 2, 3, testing, testing. Doop, 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 doop. I'd like to apologize in advance for the video here. It's terrible. I don't know why it's terrible. I log in, I open up OBS, and it's like the video is small, and when I expand it, like the colors are all off, and I tried fixing it as best I can, and, you know, that's kind of just the way of things. If you guys would please give me a shout out in the chat just to make sure that chat is actually a thing that is working, and I don't think I have it in the wrong thing, but you know, you never know with these things. Also, ooh, let me test. Just to see if we're still audio synced. A little bit laggy. A little bit laggy. Maybe that much. That's good. All right, cool. Right. Cool. Hello, everybody. Welcome back. Hope everybody had a decent time. I hope you guys aren't completely dying from your midterms that you probably have this week. Oh, I need that. So annoying. There we go. Cool. Good to see. So, my goodness. Ooh, one thing before we get started. I found this and I thought it was really cool, so I want to share it with you. If you take a look in OBS, there's actually a slide bar for hue, which is kind of fun because this is the effect. You can change colors, which is kind of fun. So I think today I'm going to be teal. There we go. You'll have to deal with a teal professor. If this is annoying for anybody, if I get 3 complaints that me being teal today is distracting you from the lecture material, I'll change it back to regular. But I thought it was fun. I think it might be fun in the context of, you know, the upcoming Halloween stuff to have like blue professor. So there you go. Smurf. Welcome to Smurfland. Who says we don't have fun? So, anyway. Also, it's the cheapest way of changing the color of my headphones. Pink Krakens, yes. There you go. Like a really purpley pink, too. But anyway, so, couple of important things that we should talk about before we get into the lecture material for today. There were some announcements that I made over the break, and I'd just like to go over those if you guys haven't seen them. So we were kind of originally scheduled to have a test at the end of this week. I have pushed that back 1 week, so I apologize for pushing it onto Halloween itself, but what's scarier on Halloween than a test, I guess? The due date for Assignment 3 is not going to change. That's still going to be this Sunday, so Assignment 3 is released, so if you guys would please do Assignment 3, we'd all appreciate it. But yeah, and I just in that message, I went over the procedure for the test. I'll go over that. You guys can read that if you like. I'll be going over it in lecture a little closer to the day of the test. I know we haven't had a test in this class yet, so I hope you guys aren't stressing too much. I will make specific efforts not to kill you guys with the test. But yeah. So, I think that's everything. Yeah. Okay. So, we were talking about pointers. Pardon me. We were talking about pointers before we left for the break, and your professor left to have his wisdom teeth removed. I still have the stitches in my mouth, by the way, so if I'm not speaking as clearly as I usually do, it's because I can't open my mouth as wide. Although it's a lot better than it was yesterday and the day before. But, yeah. Anyway, so we were making our way through the lecture slides on pointers. We were about halfway through. I'd like to skip ahead and then skip back again, because this last section on Malloc, that's dynamic memory allocation, and you guys will find that to be extremely useful for the assignment which I've assigned you guys for this week. So I think I'm just going to cover it, going to cover that material, not leave it any longer, and then we'll come back to pointer arithmetic and function pointers. Sound good? I hope so. You don't get a say. Ha ha. When are the assignment solutions going to be posted? As soon as your professor gets around to it. Let me just get it to post A1 and 2 solutions. That's on my to-do list. Now, is the test going to be like questions and answers, or code this thing, or both? So, generally speaking, I have a strong preference for code this thing type questions. You guys are in an engineering program. Engineers build shit, and in order to have graduated from an engineering program properly, I feel that you should be tested on your ability to build shit. So, asking you to build stuff is what I'm going to do. I suppose I shouldn't use words like that on stream, because YouTube might demonetize the thing that I'm not getting monetized, eh? But anyway, we'll try to keep things family-friendly, even though that's a very mild swear. So, as an instructor, I have a strong preference for code this thing type questions. However, in the examination of the accreditation requirements for this program and this course, there are certain classes of questions which I have to include in order to maintain good accreditation standing with the Professional Engineers of Ontario. I'm definitely not ruling out the possibility that there will be question and answer type questions. Probably, if there are multiple choice questions, they will be of the form, make the return value of this function what your answer is, so that we can use the auto-grading system that we've been developing in order to automatically grade the multiple choice questions, which is hypothetically the least complicated thing we're going to be asking it to do. The multiple choice questions might be a little bit weird and look like coding questions, but it'll just be multiple choice, just in a different format. Think of it in the same way as like a Scantron requires you to fill in the bubble. We're going to require you to have the return value of a function be a particular thing. But multiple choice questions, very likely to appear on the test, because they're somewhat irreducible and they're irreducible from the evaluation requirements from this course, so they'll probably be in there. I will say right now that when I am given the freedom to determine this question without the constraints of reporting requirements, I normally tend towards the almost complete exclusion of these types of knowledge questions and focus almost entirely on application questions because I feel they test you better. But that's kind of, neither here nor there. I don't like this model of education as a game show. But, But then again, whatever. You guys, that's way more answer to that question than you guys were probably looking for. Okay, so let's talk about pointers. Come on, link me up, hook me up. There we go. All right, so let's talk about dynamic memory allocation. So up to now, our array sizes have been hard-coded. That is, set in the program itself, not determined at runtime. Whether you are including a number, let me bring up code that illustrates my point. That's not really what I'm looking for. Did I put it in the slide folder? I think I probably put it in the slide folder. Sorry guys, give me 2 seconds. Yeah, so regardless as to whether you are, putting a number in there and specifying the size of the array, or you're leaving that blank and allowing that information to be inferred from the initialization of that array, we have been working with fixed array sizes. These are both determined when you're writing the program rather than at runtime. So we consider these to be hard-coded because it doesn't matter the conditions under which the program is run don't matter. The size of the array that has been allocated will be fixed at that particular value for all time, eternally, so there's no way of changing it. In this section, we're going to learn how to allocate memory dynamically, allowing us to expand or contract arrays as needed at runtime. So when we use static arrays, these memory operations are implicit. So we're going to go through a few functions. These are memory operations, and when you're using an array in the manner that we've been using arrays so far, like here and here, calls to these functions are occurring. They're just occurring in a very fixed way. We're going to learn how to use them in a dynamic way. These are called static arrays, by the way. So the opposite of static is dynamic. I think I had a slide on that at some point. Anyway, the general procedure is to declare a pointer, invoke a memory allocation operation, and store the resultant memory address in the declared pointer. So the general form for these functions that allocate memory is you invoke a function, you tell that function how many bytes you want allocated, and you receive from that function a pointer to the memory chunk that you asked for, if the operation succeeds. These functions are so fundamental that they are stored in standard library.h. There's actually one, there's one down here that got cut off. because your professor included an extra space there for some reason. But the four functions that we're going to talk about in this section are malloc or malloc, that stands for memory allocation, free, calloc or contiguous allocation, and realloc, which is just reallocation. So, malloc. Dynamic allocation of a single large block of memory given a specified size. So, in this declaration, we declare an integer pointer, we cast it as an integer pointer, and we invoke malloc and we give it as an argument 100 times the size of an integer. This means that we are allocating space in memory for 100 integers. It is not strictly necessary that this be the size of int. If you want, you could hard code a 4 in there. The purpose of doing size of int is to make this program compatible for future operating systems that might support larger integers than are supported in current operating systems. That's why using size of is generally preferred to just indicating the number of bytes, like, normally in C integer is 4 bytes, but if you put a 4 in there, then it's 4 bytes regardless of what integers might be in the future. So, malloc accepts as an argument the number of bytes to allocate expressed as an integer. It produces a void pointer, which may be typecast to the type of pointer you wish to store the address in. So, I'm not sure, did we talk about void pointers? Maybe we did. Let me see if we talked about void pointers. They might be in arithmetic. Yeah, okay. So, I'll just do this slide since it's relevant. So, there are what are called by me, and not many textbooks, wildcard pointers. Normally, pointers require compatible types to be assigned to each other. So, you can't, for example, assign a float pointer. You can't assign a pointer value, which is a float pointer, to an integer or a char, for example. The exception to this is the void pointer. Not without casting, anyway. So if you use void instead of int or float or char, then this means that you have a generic pointer that can point to any data type. Basically, all that's doing is leaving out the bit width information that is provided by the type declaration for all other pointer types. A void pointer is compatible with all data types and may be used in assignment operations freely. The catch is that a void pointer may not be dereferenced. So, obviously, since malloc is returning a void pointer, and, dereferencing pointers is how you actually get to the values that are stored at the memory addresses that the pointers point to, and seeing as that might be a thing you might want to do at some point, otherwise why would you allocate the memory in the first place? In order to do that, you should cast your void pointer as whatever pointer type you want there. And the reason that you can't dereference a void pointer is because in order to dereference a pointer, you have to know what bit width in memory that dereferencing operation needs to occur over. Like, if you are dereferencing a character, that means that you're getting the computer to give you back 8 bytes. If you're dereferencing an integer, you're getting the computer to give you back 4 bytes. It's like start here, 4 bytes, right? So if it's if it's a void pointer, it's like start here and I don't know how many bytes. It's like, well, C will say to you, well, that clearly doesn't make any sense. Come back to me when you know how many bytes you want. So, casting as some other type of pointer is telling it how many bytes you want. Yes, so this is because the dereferencing operation uses the byte width or bit width of the pointer's data type to select the area of memory to return. So there you go. That's void pointers. So, Malloc returns one of those. Malloc may fail if the requested memory is larger than the available memory. So you can imagine a situation where you've asked for some extremely large amount of memory. Perhaps you could conceive of a situation in which you ask for more memory than your computer actually has. That's difficult these days given the size of computer memory. You can imagine it was much more possible back in the 90s when the amount of RAM that you would have in a computer might be measured in kilobytes or megabytes. If you can even imagine such a situation being the case, the Malloc operation might fail. If it fails, a null pointer will be returned rather than a pointer to a specific memory address. Fortunately, we can always check this using an if statement. This is the sort of thing. Once again, this is the sort of thing where you have to do the behind-the-scenes work that makes everything work. Asking for a pointer from Malloc and not checking to see if it's given you a null pointer it's a problem that probably won't manifest itself in any of your tests of your program, but is still definitely a problem. It makes your program unstable. Because, obviously, if you try to dereference a null pointer, you end up with a segfault. I have a question. Questions? Do you need to cast to extract data? Could you extract every byte under the pointer and divide them into groups of 4 to grab an int? Well, the issue with that one would be defining a data type that is the size of your array in terms of its bit width. I don't think that would be impossible. But hypothetically, yes, you could. I'm not sure, because I'm not sure how one would go about defining a data type that contains, say 128 bytes. Such a thing does not exist natively, to my knowledge. It would be like a long int, or something like that. Hypothetically, though, there must be some way of doing it. Although you might have to go into the kernel to be able to do that. And if you were to do that, then you could extract everything that's in the array as one value, and then you would, perform bitwise extraction, like bit masking or something like that, in order to get out each of the individual values. From that, basically at that point you're reproducing the computer itself, so I would recommend, rather than attempting something like that, which is very difficult and probable, shall we say, probability of failure very high, just use the mechanisms that already exist in C to perform exactly those operations. Like, if you are extracting your data in one huge chunk and then dividing it up into integer-sized pieces afterwards, why wouldn't you just make it a group of integer-sized chunks from the beginning? But yeah, hypothetically possible, but not recommended, let's say. But yeah. So, Malloc broken down. If we have int star pointer casting as int star, Malloc 5 times size of int. Size of int is, of course, 4 bytes. The pointer then points to 20 bytes of memory. A large 20 bytes memory block is dynamically allocated to pointer. So, in a lot of ways, this is similar to if you were to convert this dynamic thing to a static declaration, you would have it as like int foobar 5. That's the equivalent for static arrays. However, the power of this technique is not, that it's a much longer way of doing a static array declaration. The point of all of this is that this bloody guy can be a variable, or an expression, or anything you like. So, because you can include variables in this expression, the values of the variables change dynamically as the program is executed. Obviously, that's the point of variables. So that means that the amount of memory that you allocate can change dynamically as you run your program. You can calculate, you can make the result of some calculation, how much memory to allocate to an array, and then you can create that space in memory and get a pointer back. It's very cool. So, we have learned how to allocate memory. Now let's talk about deallocating memory. Again, this is something that's done automatically for you when you're working with static arrays. Static arrays, however, are stored in the stack, and things that are allocated to Malloc are stored slightly differently. Do I have in the slides where things are stored? Well, anyway, it's not in the stack, it's somewhere else. So, memory manually allocated using Malloc must be deallocated manually as well. To deallocate memory is to take memory allocated to a program and return control of that memory to the operating system. If you don't deallocate stuff that you have allocated using Malloc, that stuff gradually builds up in the operating system and can cause what's called memory leaking. When a program doesn't deallocate all of the memory that it allocates, that memory sort of accumulates as reserved in the operating system, but the programs it's been reserved to are no longer, like those have been terminated, but the memory is still allocated to them. So you basically have this dead area of memory that gradually accumulates the longer your operating system has been running. And that's why it's not so much a problem anymore, because, people have understood the problem for a while, and because people have been adhering to the good programming practice of deallocating the memory that they allocate their programs, this isn't as much of a problem as it used to be. But back in the 90s, if you had a Windows 95 machine, you might have to restart that machine certainly every day, sometimes several times a day, because the computer would get too slow. And the reason the computer would get too slow is because the amount of memory that was allocated but not deallocated would increase gradually as the day wore on, as you used the computer and ran programs, and eventually the working memory of the operating system would get squeezed down and squeezed down and squeezed down until it had to start caching essential operations to the hard drive. That's sort of the last resort when your computer runs out of memory, is it starts using pieces of your hard drive instead of RAM. Obviously, this takes a heck of a lot more time than using the RAM. That's why the RAM is the RAM, that's why it's called RAM and not ROM. So you would restart your computer, that would reset the RAM. That's like a full deallocation of everything that's in the RAM, and then you would just keep building up again, and you'd have to periodically restart. So that's why it's important to deallocate memory that you allocate. It's kind of in the same category as closing file streams that you open. If no program deallocated memory it used, you would have to restart your computer very frequently. The free function accepts a pointer as an argument and deallocates the memory pointed to. Once again, it's kind of similarly to how size of only works within the context the pointer has been created in. Free should also only be performed within the context that the pointer was created in. While it is not enforced by the compiler, freeing dynamic memory is the same as closing file pointers, very good practice. So, it's considered the height of good manners. Pardon me. Anyway, good. So this is how free works. If we have allocated a space in memory, and that space of memory, for example, is 5 bytes, or 5 integers, which means it's 20 bytes, if we perform some operations on it, and then we're done with it, if we call free, those pieces of memory are put in the trash bin. It's not quite this. It's definitely not the same thing as like the recycle bin on Windows. The better way to think of it is that the operating system keeps a table of what memory has been allocated to which process, and it removes the entry in that table so that the operating system can use it for other purposes. The memory is not overwritten by free. That's so if you're wondering where all of this junk data that we've been talking about comes from, it's memory that has been allocated and then deallocated, but not wiped, because deallocating memory is removing an entry in a table. It's not actually overwriting with zeros or anything like that. Question. Does the allocated memory remain until the program is terminated or until we restart the system? The allocated memory stays until you restart the system. It's not stored in the stack. If it were stored in the stack, then it would be deallocated when the stack frame is deallocated, right? The same as any other automatic variable. However, because it's being stored in memory other than the system stack, because that's where Malloc gives you the memory, it stays there until it's either deallocated or everything is deallocated during system restart. That's a good question. Thank you for your question. So, here's an example using Malloc and free. If we have a function, malloc demo, takes an integer. We have an integer pointer. Oop, I forgot to cast it. Oops. Sorry about that, folks. That's a slight error in the slides. This should be cast as an integer pointer. Malloc n times the size of an int. If pointer is equal to null, printf runtime error, then return nothing. Printf the memory location allocated is that for every element in that pointer. We assign it to the value of I. We then print the array. I should have this program kicking around in the code folder, so we'll take a look at it. Dynamic.c, that seems like a good candidate. Okay, yeah. Oop, that's realloc. But, okay, there's Malloc. So, if we run this program, and did I fix? Let me just fix that right there. Good lord. So apparently it works without that, but anyway, gcc wall dynamic.c. If we run, a.out is what it puts the executable in if you don't specify a name. The memory address allocated is thus. The allocated array is 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., all the way up to 29. There you go. But notice a few things. Number one, notice that we are checking to see if we're getting a null pointer returned from Malloc. Number two, we are freeing this memory when we're finished with it. Both important points. So there you go. Oh my goodness. Stop! There. So, let's talk about Alloc. Memory allocation for the hygiene obsessed. Calloc is an alternative to Malloc. It accepts two arguments. The first is the number of chunks of contiguous memory to allocate, and the second is the size of these chunks of memory in bytes. So whereas with Malloc, our form was to just give it one integer and to multiply the number of chunks we want by the size of those chunks, in Alloc's case, those are just the first and second argument. Additionally, Alloc wipes all allocated memory. Everything is set to 0. That's why it's memory allocation for the hygiene obsessed. There is no possibility when using Alloc of receiving smelly garbage. It initializes everything to 0. Aside from this, usage is exactly the same as Malloc. It still returns null if the memory was not allocated. It should still be freed using free. All of these things, and it should still be cast, even though, again, I forgot to do that in the slides. Sorry about that, guys. Alloc is slower than Malloc, however, as overwriting the allocated memory takes time. You can think of it as, because you're performing an overwriting operation, you have to perform an overwrite operation for each chunk of data that you're overwriting to, so you would introduce a number of operations proportional to the size of the memory that you're allocating, so it's like a big O of n situation. Here is green boxo vision for Alloc. You can see it works in pretty much the exact same way as Malloc. So let's talk about Alloc. So far we've talked about how to declare and destroy memory, allocate and deallocate memory. Declare and destroy is perhaps a little bit dramatic. Alloc allows us to change the amount of memory allocated to a pointer while keeping the data already in it. So if you have declared a certain amount of if you have allocated a certain amount of memory to a pointer and you want to change how much you allocated to it, you use Alloc. It changes the size. So, for example, if we declare a int star pointer with Alloc of size 40 and we want to later change that to size 100, we would use Alloc. The first argument to Alloc is the pointer that you want to reallocate, and the next argument is the amount of memory you wish to change it to, in the same manner, and this follows Malloc conventions rather than Alloc conventions. Ugh. It might be that 2 hours of speaking is a bit much for a person who had his wisdom teeth removed recently. Sorry, guys. We'll get through the next 10 minutes. The second argument is the new size following Malloc rules. Yeah, I just said that. Realloc returns a pointer to the newly allocated memory. So there are some situations in which the pointer may not change. However, in the overwhelming majority of cases, count on this pointer being different. Like the memory address will change, and that makes sense, right? If you are expanding the amount of memory that you are allocating to the pointer, you are probably going to have to move it somewhere else because there's probably stuff at the end of it. So yeah, new chunks of memory will be filled with smelly garbage. So realloc does not overwrite with zeros in the way that calloc does. So just keep in mind that you will have garbage data. Probably in the case of downsizing a pointer, it maintains. It probably just keeps it in the same place because that seems a lot more memory efficient to me. But if you're allocating more space, it'll probably end up somewhere else. So realloc. If we allocate 20 bytes of memory to the int star pointer, and we reallocate 10 times size of int to pointer, the pointer we end up with has 40 bytes of memory. The important point to realize, however, is that the data that's contained at these memory addresses will be preserved, even if the pointer has moved to a different point in memory. So if the pointer, if the chunk of memory moves locations in memory, all of the previous values will be copied over to the new location, so you're not losing any data, which is important. So here's a, I've got a question. Let me take this question before we talk about this example. We don't need to worry about the previous pointer being deallocated, or does realloc do it automatically? I imagine it does, but let me check that. That's a very good question, and I don't know. Google. Does realloc free old memory? Good question. So this is from CPP reference. This is also a C++ operation, by the way. Or we could just ask Stack Overflow, see which comes. Reallocates a given area of memory must be previously allocated by Malloc or Calloc or realloc, and not yet freed with a call to free to realloc, otherwise results are undefined. It does not seem as if it seems. Oh, all right. So, So in the event that realloc fails to allocate new memory, it will not free the old memory. It won't destroy the data if it fails to perform the reallocation. So you may need to free it. But if it successfully allocates the new size memory chunk to the point and produces a new pointer, the old one is freed. So that's the answer to the question. Good question. Very good question. Can realloc be used to make pointers smaller? Yes. Yes, it can. My particular example is, I think, making them bigger, but, you know, that is what it is. So, in dynamic, if we run the realloc demo rather than the malloc demo, in this case, we are allocating a array of 5 integers to pointer, basically, or we're assigning a chunk of 20 bytes. We assign each of those a value. We then reallocate that memory to double its size, and then we're going to print it and see what's in it. So, save that, run that, execute, there we go. So, this is the old address before reallocation. Our new address, you can see, is in the same neighborhood, but off by quite a bit from the old one. And the old values are maintained, the zeros are here, but I wouldn't count on that being the case every time. Although it seems to be the case every time. I don't know. It's possible that GCC's particular implementation of realloc does overwrite, but you should not assume those values are going to be initialized. You should assume that they're going to be smelly garbage data. So there you go. Okay. Oof. I apologize for this. So yeah, output, we saw it. Oh, you guys don't get the last slide comic until we're actually done this presentation. Anyway, so that's Malloc. That's going to be super useful for you guys doing the assignments. So let's continue on with pointer arithmetic. I already talked about that last time. So, here is a program illustrating array addressing. So, do I have this one in here? Is this it? Yeah, this is it. So, if we have a yeah, okay, I get what we're doing here. Oh. So it's arrays. So what this program is doing is it's showing us what the values of, what the pointers are, what the addresses are of subsequent pointers in memory. I apologize. Let me rephrase that. What we're taking a look at are the memory addresses of adjacent indexed values inside of arrays. So 0, 1, 2, 3, 4. You will notice that foo, which is typed as an integer, you'll notice that the memory addresses for these elements are offset by 4 each time. This should, since we know that an integer is 4 bytes in width, this should indicate that these pointer addresses are addressed to the byte. Similarly with bar is a short int. That means it's 2 bytes. And you can see that our offset here is in fact a 2-byte offset each time. So there is a numerical relationship between these address of operators and the actual memory addresses. There's actually a direct relationship between them. In fact, as we're going to see, this address of operator is syntactic sugar for pointer arithmetic. So you can see when we have a pointer, it points to the first element in an array, and each element of the array is some fixed number of bits later down in memory. So, it's 12:20, time to stop, my mouth hurts. I'll take any questions that you guys have, but if you guys don't have any questions, I'm going to go get some lunch, and maybe also an aspirin. Actually, it's ibuprofen. Incidentally, we managed to have our first quasi-successful execution of the auto-grading system that we've been working on, and it managed to more or less successfully mark 90% of the questions for assignment 2. So that hopefully it won't take the TAs as long to get through only 10% of the workload. But I generally consider it to be a roaring success so far, and Mark has been exceptional in his development and his work on that. Cool. All right, well, there don't appear to be any questions. If you have any questions, you can hit me up through the usual channels. And yeah, okay, that's cool. Thank you very much, everyone. I'll talk to you guys later. Bye.